Hi there, we're the baseball team. My name is Ethan.
I'm Luke.
I'm Allison.
I'm Jonathan.
And I'm Alec.
And today we're going to be talking about our high-speed baseball launcher. The sponsor for this project is J.J. Ruby of the Houston Astros. For the abstract of this project, our task was to design and manufacture an apparatus that launches official Major League Baseballs into stationary bats at high speeds. Our final design consisted of a spinning arm that housed the baseball with a release mechanism that gets triggered by a steel cylinder. The final design failed to meet the specified speed and travel distance requirements, but it did successfully pass the cycle time and radial variation requirements. Resonance occurred at around 450 revolutions per minute, and this prevented us from testing at higher speeds.
So it's currently unknown how bat properties such as moment of inertia affect a bat-ball collision, and measuring that energy transfer will yield useful data for the Houston Astros and provide insight into which bats are best for hitters to use in games. Our baseball launcher will help determine exit velocities, therefore finding the transfer of energy between the bat and the ball during collision.
At the start of this project, we worked with J.J. Ruby to determine some deliverables, requirements, specifications for this project. Some of the deliverables included the ball throwing device or baseball launcher, a theory of operation manual that tells the user how to use the system, and a final report including launch data. Some of the requirements for our project included using a standard Major League Baseball and baseball bat, as well as a high-speed camera to record the collision. And then some of the specifications included the exit velocity of the ball from the launcher had to be variable between 100 and 175 miles per hour. The radius of variance for the baseball impact on the bat is half an inch. The maximum time between launches is 1 minute, and the ball travel distance is 5 feet of observable contact. So for this project, we had to run a number of analyses for each part of the project. And these included a fatigue analysis on the release mechanism, which was made out of aluminum. And the fatigue analysis showed that this release mechanism would break down over time and have to be replaced after a number of tests. Another analysis we ran was looking at the torque we needed to apply on each fastener. And the standard fastener we used in this project was a 1/4-20 steel head socket screw. And we found that the torque applied to each screw should be 4.7 pound-feet. And then in the initial design of the baseball launcher, we had a counterweight to balance the back of the arm from the weight of the release mechanism at the front of the arm. And we found that after having a 9-pound steel cylinder on the back of the arm on a 1/4-20 threaded rod, the force when spinning at 175 miles per hour, the force applied on this rod would be way over the yield strength of this system. So we had to replace and upgrade the counterweight.
Based on similar math to the counterweight, we were able to find out that the baseball, even though it's 5 ounces, equals to a 500-pound force on the system at the 1750 RPM. Based on this, we were able to do finite element analysis simulation on all of the release mechanism parts to ensure that they would not break under yield stress at these speeds. Due to this, we were able to modify the design to get it under the yield stress, and then furthermore, we were able to do some optimization to make the pieces as light as possible for the initial design. Unfortunately, simulation can only get you so far, and then we had to take these designs to get tested to figure out more. So the initial design, as Ethan had described earlier, is the rotating arm with the release mechanism that houses and lets the ball go after hitting the steel cylinder. So after manufacturing this design, we were able to reach a speed of 200 RPM as our max speed, but this design still gave us valuable insight into the workings of the release mechanism and counterweight specifically. A couple of issues that were addressed was the idea of us not being in the path of the steel cylinder of the solenoid and having to adjust the release mechanism to hold the ball more securely.
So while the initial design was capped at 200 RPMs, the final design was capped at around 450 RPMs. In addition, there were improvements to our design, ergonomics, and functionality. So to start with our couple, the set screw was put in a more ergonomic location, which allowed for more easy tightening. In addition, the height was decreased, which allowed the arm to spin more closely to the top of the motor structure. For the release mechanism, the ball was now held more towards the center of mass, which allowed for the arm to spin more evenly at high speeds. For the counterweight, there was more secure attachment compared to the threaded rod, and additionally slots were added to allow for the position to be manually changed so that the arm could spin evenly throughout the process. For the bat holder, a variable position technique was used that allowed us to test different collisions at different locations on the bat. And for the solenoid extender, we added a thicker steel plate which increased the durability and lifetime of our solenoid extender.
All of our tests were conducted in the Taylor machine shop, and you can see the setup in the picture to the left. We enclosed the structure with metal cages to provide safety for observing, and high-speed video was used and post-processed using MATLAB to determine the exit velocity and location of impact for each collision, and an image of that can be seen at right.
Here are the results of our test. We performed our test in 2 sets. The first one targeted a launch RPM of 300, and the second one had a launch RPM target of 400 RPM. The second test also was recorded at a higher frame rate of 2,000 frames per second versus 1,000 in the first set, and that may also had impacts on the accuracy of the observation of the ball flight. As we can see, the speed before the collision is roughly consistent at a targeted launch RPM, and seems to roughly scale linearly with the launch RPM as well, where the speed after collision is a little bit less consistent in terms of observation. A nice thing here is that the balls were hitting in a consistent location, so that means we passed our radius of variance for the ball impact on the bat, and it was really nice because we were also able to see the ball every single shot if we had ours set up correctly. Also, the test only took about 9-10 seconds for spin up to launch the ball, so it definitely was able to pass the 1 minute of time between baseball launches because it only took 10 seconds to launch the ball. However, unfortunately, as explained earlier, the launcher could not safely get up to speeds greater than 450 RPM, which would be about 45 to 50 miles per hour in terms of ball speed. So we were not able to reach our ball speed specifications. And also the camera field of view was very small, so we cannot watch the ball for more than a few inches in here, so we can have that much distance of observable ball flight. In the future, you have 2 main goals of improving the structural integrity of the launcher and also improving our ability to observe the ball flight. So obviously we want to change the structure such that it will increase the resonant frequency such that we can reach those speeds that we were targeting when we initially took on the project. You also can see here on the right that the top is the piece of this that hits the release mechanism to trigger, and that got bent by getting hit by the release mechanism, so it's very clear that the stress there is very high, and also the release mechanism has a bit of chipping on it as well. So we would want to redesign these parts to reduce the amount of contact stress there is between them. And on the bottom is a bolt that held the counterweight on, and this one has been redesigned but to reduce the loads, and now we have a more secure connection in that area. So generally all around we want to try and increase the stability, whether it's having the rotational axis be more aligned or having the connections be stronger. Also, part of the reason why the speed after contact was variable is that we only have 1 camera, and that camera can only view motion accurately when it's like in plane perpendicular to the camera's viewing motion. So if we have another camera set up on an orthogonal like axis to that camera, then we would be able to see the full ball flight of the ball after collision, which would give us the full data on the speed after contact. So that's definitely a big area that we're trying to look to improve, as well as in order to improve, reduce costs, we could transition to a fully Arduino-based system. This current system runs off of National Instruments hardware, and as well as MATLAB, which costs a lot of money for upkeep. So I think it's possible to switch to Arduino, and it would reduce the cost if you could do so.
We would like to thank the following people for their assistance and contributions to our project. First and foremost, JJ Ruby, our sponsor. We're very appreciative of all his meetings every week in addition to providing insight and multiple physical attributes of our structure, which were very helpful. And Professor Muir assisted in designing, manufacturing, and testing throughout the whole semester. Bill Mildenberger machined and oversaw us machining numerous parts that were essential to the functionality of our launcher. And Chris Pratt lent her expertise in operating the plasma cutter as well as the water jet. Sam Kriegsman both helped source electronic components as well as data acquisition devices, in addition to helping us with ideas in the machine shop. Alex Prideaux ordered all of our parts and helped configure the high-speed camera as well as the software. And Jim Elkins assisted and oversaw our manufacturing in the Retner machine shop.
Thank you for watching our presentation. For more details on the project, look at our webpage.